Next up, we have Quentin Anthony, who is their model training lead from Zyphra. Come on up. Let's give him a round of applause. There we go. And we're going to talk, so the first presentations were about what people are doing to overcome the CUDA model. This is what people are doing beyond CUDA on the pre-training side. Quentin, take it away. This is yours. Oh. And then just use the green button.
Okay, thanks. Does this work? Okay, awesome. So thanks for the intro. Yeah, I'm Quentin Anthony. So I'll be talking a lot about what Zyphra's doing. Sorry. We're working a lot on AMD GPUs, so let's go into detail. So, yep. Okay, so I'm going to be talking a lot about a paper that talks about model sizing specifically for hardware. So we at Zyphra are trying to pre-train from scratch like a spectrum of models that match the spectrum of compute. What does that mean? You have cloud GPUs, for example, MI300 or MI325. And then, for example, you have everything going from on device, so sort of like Snapdragon, Samsung phones. We have different model sizes for each of these, and finding efficient kernel paths for each of these is a big problem. Go ahead. Oh, okay, cool, thanks. So paper on the left, and then link to Zyphra on the right. So let's get started. So transformer LLMs are composed of GPU kernels, we all know this, and those different kernels have different sizes that they like, that are more amenable to the GPU hardware. So beyond just tuning those specific kernels via cutless and cuBLAS, GPUs are fundamentally more amenable to some model sizes. So you might remember this tweet by Karpathy finding that just rounding the vocab by padding it with some dummy tokens gave them the most speed up compared to everything else. So consider just neurons in a hidden layer, right? So between 2 to the 10th, so 1024 neurons versus 1023, you can get massive slowdowns just by a difference of 1 neuron. So model accuracy is not going to be affected by a single neuron in each hidden layer, but your efficiency is. So finding efficient sizes is especially important since model designers tend to really copy structure. So for example, in this chart on the bottom right, we took the GPT-3 model for 2.7b, and we found that many other competing companies trained similar models, pre-trained them from scratch, and they just copied the model dimensions from the GPT-3 paper. But this is a very inefficient size. So just by rounding the number of neurons in your hidden layer, everything to your attention dimensions, which we'll talk about in a bit, all can really improve your performance. Okay, so a bit more about sizing. So treat transformer models as a sequence of GPU kernels, and then what kernels take up a single layer's latency. So we looked at we're talking about transformer models, so they have attention, they have MLPs, they have layer norms. Where is that time being spent? So we're seeing that, as expected, as model size grows, the majority of your time in a single layer is from gems, from attention, and then the MLPs specifically. So that should be an arrow, but H to 4H and back from 4H to H MLPs, that's where a lot of your time is spent. So I'll direct your attention to the bottom left stacked bar chart. And then on the right, we map these exact kernels. So we're sort of looking at models as kernels. Okay, so now that we know where the time is spent, we should be looking at the MLPs and the attention. What are the sizing behaviors of each of those? So the good news is that the MLPs, where the actual time is being spent, those sizes depend just on factor of H, the hidden dimension, and 4H for our example, which is really easy to make divisible by 64. So you're done, and then it's just a roofline model. So you just need to make sure that those MLPs are big enough to saturate your GPU being A100, H100, MI300X, whatever it is. As long as it's big enough, you're fine. The only MLP constraint is capacity, like I was mentioning. So we actually at Zyphra have lookup tables, one for each hardware. So if we're trying to define a new model, it needs to be 4 billion parameters. Then we'll look, okay, what's most efficient for Snapdragon? What's most efficient for MI300X? And the good part is that a lot of these have sort of sizes that rhyme. And finding the size that is at the peak for every single hardware is what we're doing, and it's what's baked into all the models that we have today. So then when you run inference for any of our models on any of these hardwares, you already get baked in best performance. Okay, attention is a bit of a different story. So first I'll talk about in the Stone Age before flash attention. It's just kind of instructive to show what I'm talking about. And then in a bit we'll get into what are the actual performance, or behaviors of flash attention specifically. So for attention we can see we have these we have 3 ranges of peaks, right? So we have these really high values, then we have a sort of an intermediate, and then we have these very low performing hidden sizes. And these relate to factors of, well, let me show you the next slide to show you what those are. So two most sensitive kernels for non-flash attention calculation is the attention scores over values, and then the query key value transform. So these two separate gems, and they each have their own behaviors. So these kernels are much more sensitive to model size. So you might look at the kernel sizing like table on the bottom left, and you'll see that they have factors of h over a. So h is hidden dimension, a is the number of attention heads. It's really easy to have like factors of 64 in h, but in h over a, things get a bit more complex. We also have factors of t, which is tensor parallel. So once you do more and more model parallelism, you have a lot of different sizes of gems flying around, and making sure that every single size is efficient on the GPUs that you're training on and tend to eventually inference on is the problem that we're trying to solve. So the gist here is that, first off, you need to ensure that h over a has as many factors as 2 as possible. If you recall from the previous slide, h over a having a factor of 8 is like the peaks, the very highest peaks, and then the middle peaks are like factors of 4, and the bottom peaks are factors of 2. So just as many powers of 2 you can have as your factor for h over a, the better for your model. Let's see, preferably have h over a divisible by at least something like 64. So that solves like, I believe it's the attention over values, but then for what are these waves that are showing up? I want to drill down a bit on those some more. I don't know if animations will work here, but a little bit of background, and alternatively, why are GPUs so amazing for parallelism, is that GPUs are composed of streaming multiprocessors. Each of those SMs are filled with a lot of tensor and CUDA cores, and then you schedule warps to them. So those SMs contain warps, and they contain cores, and those SMs run in parallel, so it's all SIMD. The goal of us is to keep all of these cores busy. So if you just have a single core spinning on every single SM, NVIDIA SMI will tell you you have 100% utilization and everything, but it's not really like you have a lot of cores idle. So you want to keep all SMs busy, and not only that, you want to keep all the cores within all the SMs busy. Okay, so I think that's all I want to talk about here. So then, why is wave quantization showing up, and why do we care? So if you just have a single unit of work, you just post it to a single SM, and you get some smaller occupancy. Oh, okay, there we go. And then I don't think my animation is showing up properly. It's not, there should be a line, so you just have to sort of take my word for it. But each time that you are posting a warp to an SM, you're doubling your throughput, right? Until you reach capacity. So let me go back a little bit. So single SM, single warp, so you just have a throughput of 1 T-flop, for example. And then you double it. So you double your occupancy because you're still just filling up SMs and everything's happy. You're just linearly increasing until you saturate all of the SMs on your GPU. What happens if you have a new like SM's worth of work to do, but all your SMs are already full? You schedule another time step. The problem is that when you schedule another time step, that second time step, all the SMs will be idle except for the one additional set of warps. Let me go back. Yeah, but fighting with the animations a bit here. But then this results in waves. So anytime you have time steps where SMs are not full, you have like your wave starts to go down. And then eventually these sort of periods will get smaller and smaller, and you'll reach saturation. But this does explain why like the number of SMs in your GPU, whatever that GPU may be, is relevant, and the number of like units of work. And for flash attention, units of work is like an attention block. So I think I'll skip through. I've already talked through these. The only part I want to mention is the last one. So for like flash attention, you have like these two axes, the batch axis and the number of heads A, and you just want to make sure that that number is divisible by the number of SMs. Let me step away a little bit there. Okay. So a bit more on that. So as thread blocks are scheduled to these SMs, only a finite number of thread blocks can be scheduled at once. So for example, if you have 108 streaming multiprocessors and you have 109 thread blocks, then you'll be into the next wave and your throughput will decrease significantly. How do you resolve this? So flash attention has a nice two-stream design where they have two attention blocks running, and the second stream will post attention block operations to those idle SMs so that you no longer have this wave quantization effect, which is the figure on the bottom right. So then it's just another roofline if you're using Flash V2 and beyond. I think V2 is when they introduced this. But making sure you're on the top of the roofline is just another constraint you need to make sure you're under. So sizing, we boil things down to the following. So any model makers and also fine-tuning and inference people should be aware of what is the sizing of your model and what was it trained on, because this determines like what your max performance is. If you like padding your sequence length to a multiple of the number of SMs, which is something we've specifically had to do, then you like won't see wave quantization or stream overhead from like the flash attention. So like if nothing else, I want to like really drive home that people should know what the sizings of your model are and like which GPU or TPU, whatever else it was made for. So like when everything was, single vendor GPU, it was really easy. Like you just know, okay, all my GPUs are made with the same design constraints, but that's no longer the case. You need massive lookup tables. Okay? The paper has a full like list of what you should think about, and then in closing, given this sort of setup where everyone's training different models on all kinds of different hardwares, you need to know the difference of like what you're baking into your model. So one example here, it's cut off a little bit, but we trained a model on a 6 GPU cluster, 6 GPUs per node called Summit, and it has tensor parallel degree of 6, right? So then you need to decide if all of your hidden dimensions are divided by the tensor parallel degree 6, like do I make my model training efficient or inference efficient? And these sort of cases are coming up more and more. Like if you're training on MI300X and you're going to infer on a mobile chip or something like that, then you need to think a priori, what sizes am I training this model to be efficient for? And do I eat that cost at training time or at inference time? One example here is that even though like the Pythia 1B parameter model is larger than the 410M, it has much lower inference latency. And that's because the model was baked from scratch, the 1B model was baked from scratch to be inference efficient on this specific chip. Okay, and then just closing out that little aside I talked about for Summit and tensor parallelism, we ended up making the decision to like eat the cost of training time. So even though you have a tensor parallel degree of 6, we made the sizes amenable only if you have like tensor parallel degree of 8 for when you end up serving the model on like an MI300X node with 8 GPUs. Okay. And then just summary and future directions. With that in mind, treating LLMs as like a classical HPC problem reveals lots of low-hanging fruits. Lots of papers, like even the flash attention paper, is just like, let's apply classical HPC to this new hot thing in AI. And I think that's going to keep coming up. Small changes in the size of a transformer model, and any sort of model, we do this as well for Mamba, anything else, RWPV, can greatly affect throughput. So make sure, if you're pre-training from scratch, make sure that you think about what it's going to be trained and inferred on, and if you're doing inference or fine-tuning, then make sure you know what your model was sized for. Be careful to size your model appropriately, especially across hardware, and then in the future, we'll be like publishing a paper very soon on like across different data types, model block types, like the Mamba I mentioned, new GPUs and such. That's all I've got.